Imagine cutting a giant hole in your roof on purpose. It sounds like a terrible idea. Yet millions of homes around the world do exactly that, and the result can flood an entire room with natural sunlight. But here's what nobody tells you. The skylight above your head is one of the most engineered pieces of glass in modern construction. Today, we're going inside the factories that transform raw minerals and industrial metals into windows that can survive decades of blazing heat, freezing winters, hailstorms, and hurricane-force winds. Most people never think about this. Every skylight must remain crystal clear while standing directly in the harshest environment a building can offer. Day after day it faces ultraviolet radiation, temperature swings of more than 50 degrees Celsius, pounding rain, snow loads, and powerful winds. What happens next surprised even experienced engineers, because the journey begins thousands of kilometers away from the rooftops where these products eventually end up. The most important ingredient in a skylight is glass, and that story begins with sand. Manufacturers often source ultra-pure silica sand, containing more than 99% silicon dioxide from large deposits in countries such as the United States, Australia, Belgium, and parts of Northern Europe. Massive excavators remove thousands of tons every day, loading trucks that rumble across dusty quarry roads. Imagine mountains of pale sand slowly becoming transparent windows. But silica alone cannot create the glass needed for a skylight. Manufacturers blend it with soda ash, often produced from trona or mined in Wyoming, and limestone extracted from large quarries around the world. Together, these materials lower melting temperatures and improve durability. Think about this. A material that looks as ordinary as sand will soon survive decades on a roof exposed to the elements. Next comes aluminum, the lightweight metal that forms many skylight frames. The journey starts with bauxite, ore mined in Australia, Guinea, Brazil, and Indonesia. Refineries process the reddish ore into alumina powder before smelters use enormous amount of electricity to separate pure aluminum. The glowing metal emerges from electrolytic cells at temperatures hot enough to make the surrounding air shimmer. Rubber seals and gaskets play a hidden role that most homeowners never notice. Manufacturers produce these components from synthetic polymers derived from petroleum and natural gas. Tiny strips of engineered rubber prevent water from entering the building during years of storms and changing temperatures. Without them, even the strongest glass would fail its mission. Then there are the advanced coatings. Some skylights receive microscopic layers of silver-based low-emissivity coatings that help reflect heat while allowing visible light to pass through. These nearly invisible layers can dramatically improve energy efficiency. And this is where it gets truly extraordinary, because a coating thousands of times thinner than a human hair can change the performance of an entire building. Before any manufacturing begins, these raw materials travel astonishing distances by ship, rail, and truck. Some ingredients cross entire oceans before reaching the factory floor. Every shipment must meet strict purity standards because even tiny contaminants can weaken the final product. But the real magic begins when these materials finally enter a factory where temperatures soar beyond what most people can imagine. Millions of years underground are about to transform into flawless sheets of glass. The heat is intense. Behind the factory walls, giant furnaces glow brighter than sunsets. Raw minerals that spent the machinery is relentless, and one mistake can ruin thousands of dollars worth of material in seconds. What happens inside those furnaces is the part of the story most people never get to see. The moment the raw materials enter the glass factory, everything changes. Massive computerized batching systems weigh silica sand, soda ash, limestone, and recycled glass with astonishing precision. Even a small variation can affect clarity, strength, or thermal performance. Imagine standing beside conveyor belts carrying thousands of kilograms of material every hour toward a furnace hotter than flowing lava. Next, the mixture enters a furnace operating at approximately 1,550 degrees Celsius, or 2,822 degrees Fahrenheit. Inside this glowing chamber, the minerals melt into a liquid, so bright it looks like a river of sunlight. Powerful burners maintain temperatures day and night for years without stopping. The roar of combustion fills the building while waves of heat ripple through the air around the furnace. What happens next surprised even experienced engineers. The molten glass flows onto a bath of liquid tin heated to roughly 1,000 degrees Celsius, or 1,832 degrees Fahrenheit. Because glass floats on tin, gravity creates an almost perfectly flat surface. This process, known as float glass manufacturing, produces sheets with optical precision across enormous widths. As the glass ribbon moves forward at speeds between 5 and 15 meters per minute, it gradually cools. Rollers guide the material through a carefully controlled environment where temperatures slowly decrease over several hours. If the cooling happens too quickly, invisible stresses can form inside the glass. The process looks calm, but engineers monitor every second with extraordinary attention. A giant glass sheet then enters cutting stations where computer-controlled systems slice it into exact dimensions. High-speed scoring wheels travel across the surface with millimeter precision. A sharp cracking sound echoes through the factory as perfectly straight cuts separate the panels. Most people never think about this, but a single skylight panel may pass through dozens of measurements before moving forward. Now comes one of the most critical stages: tempering. Workers load the glass into a tempering furnace heated to approximately 620 degrees Celsius, or 1,148 degrees Fahrenheit. After several minutes, powerful air jets blast both surfaces with high-pressure air. The rapid cooling creates compressive forces that make the glass up to 4 times stronger than ordinary glass. Think about this. If tempered glass eventually breaks, it shatters into thousands of small pieces instead of deadly razor-sharp shards. That safety feature results from carefully controlled thermal stress deep inside the material. What appears to be simple glass is actually an engineered safety system. Many premium skylights go even further by using laminated glass. Manufacturers place a transparent polyvinyl butyl layer between 2 sheets of glass before applying heat and pressure. Inside an autoclave operating around 10 to 15 bar pressure and temperatures near 140 degrees Celsius, the layers permanently bond together. The result resembles automotive windshield technology designed for roofs. Meanwhile, aluminum frame production begins in another part of the facility. Extrusion presses exert forces exceeding thousands of tons, pushing heated aluminum through precision dies. Long metal profiles emerge continuously, still warm from the process. The machinery groans with immense power, while glowing metal shapes take form before your eyes. Workers and robots then cut these aluminum sections to exact lengths. CNC machining centers drill mounting holes, create drainage channels, and shape connection points with tolerances often tighter than 0.2 millimeters. Metal shavings fly through the air while automated tools change positions in seconds. Every frame must fit perfectly because even tiny errors can lead to leaks years later. Next comes powder coating. Electrostatic systems apply fine powder particles to the aluminum surface before the frames enter curing ovens operating around 200 degrees Celsius, or 392 degrees Fahrenheit. The coating melts and bonds into a durable protective finish resistant to corrosion and ultraviolet exposure. The smell of heated coatings mixes with warm metal as finished components emerge from a line. Photorealistic, cinematic, ultra-detailed, 8K, industrial documentary style. Skylight assembly line with robots positioning glass panels and technicians installing seals and hardware. Advanced manufacturing facility. Dramatic lighting, orange and blue industrial color grading, wide-angle lens, depth of field. Trapped between multiple glass layers to improve insulation. Automated filling systems inject the gas, and this is where it gets truly extraordinary. Many modern skylights contain argon gas before permanently sealing the unit. The invisible gas helps reduce heat transfer while improving energy efficiency throughout the building's lifetime. By this stage, a product that started as sand, rock, petroleum, and ore has become a sophisticated architectural component. But here's the question nobody can answer just by looking at it. How do manufacturers know it will survive decades of storms, sunlight, and temperature extremes? The next section reveals a hidden technology and brutal testing that separate ordinary products from world-class skylights. Before a skylight can reach a rooftop, it must survive a series of tests that would destroy many ordinary windows. Most people never see this hidden world. Behind the factory floor, entire laboratories exist for one purpose: finding weaknesses before customers ever do. Imagine engineers trying to break a product on purpose every single day. The first line of defense often comes from AI-powered vision systems. High-resolution cameras scan every glass panel as it moves through production. These systems detect scratches, bubbles, chips, distortions, and contamination smaller than a fraction of a millimeter. What happens next surprised even experienced engineers, because computers can spot defects invisible to the human eye. Laser measurement systems and verify dimensions with extraordinary accuracy. Some production lines maintain tolerances as tight as plus or minus 0.2 millimeters. Beams of light sweep across aluminum frames and glass surfaces thousands of times every second. A component that falls outside specification immediately leaves the production flow for further inspection. Now comes one of the most dramatic tests in the entire industry. Massive pressure chambers simulate hurricane-force winds and severe weather conditions. Engineers expose skylights to pressure differences reaching hundreds of pascals while monitoring structural movement. The glass flexes slightly, seals compress, and sensors record every microscopic change. But here's what nobody tells you. Water testing can be even more challenging than wind testing. Powerful spray systems simulate driving rain from multiple angles for extended periods. Thousands of liters of water strike the skylight, while engineers search for the smallest sign of leakage. One tiny failure can send a design back for improvement. Some skylights face impact testing that feels more like a science fiction experiment. Steel balls and specialized projectiles strike the glass to simulate hailstorms and falling debris. The impact echoes to the laboratory like a gunshot. Engineers carefully analyze the damage to verify compliance with international safety standards. Climate chambers push products to environmental extremes. Temperatures may cycle from minus 40 degrees Celsius or minus 40 degrees Fahrenheit to over 80 degrees Celsius or 176 degrees Fahrenheit. Moisture levels rise and fall repeatedly while seals, coatings, and structural materials expand and contract. What seems like years of weather exposure happens inside a laboratory over a matter of weeks. Most factories report rejection rates between 1 and 3% for premium skylight products. That may sound small, but in a facility producing hundreds of thousands of units each year, it represents a huge commitment to quality. Every rejected component carries material costs, labor costs, and production time. Yet manufacturers accept those losses because reliability matters more than volume. Many facilities operate under internationally recognized certifications, such as ISO 9000 and One Quality Management Systems, and regional building performance standards. Detailed records track materials, operators, machine settings, and inspection results. Imagine being able to trace a finished skylight back to specific batches of glass and aluminum used during production months earlier. And this is where human skill still beats machines. Experienced inspectors often notice subtle visual imperfections that computers may classify as acceptable. Years of experience allow them to recognize unusual reflections, coating inconsistencies, or assembly details that deserve a closer look. In an age of automation, craftsmanship still matters. Once a skylight passes every inspection, manufacturers package it using protective materials designed to survive international shipping. Glass, metal, coatings, seals, and electronics must arrive in perfect condition. The product now looks complete, but one mystery remains. How many skylights does the world actually produce? And how has this industry transformed modern architecture over the last half-century? The skylight industry may seem small compared to automobiles or smartphones, but its global footprint is surprisingly massive. Manufacturers around the world produce tens of millions of skylights annually for homes, offices, factories, schools, airports, and commercial buildings. Together, these products bring natural daylight into billions of square meters of indoor space. Imagine entire cities illuminated by sunlight that enters through engineered openings in the roof. Industry analysts estimate the global skylight market generates several $billion in annual revenue, with continued growth driven by energy-efficient construction. Architects increasingly use skylights to reduce dependence on artificial lighting during daylight hours. Most people never think about this, but a properly designed skylight can significantly reduce a building's energy consumption over its lifetime. Today, some of the largest skylight-producing regions include North America, Germany, China, the United Kingdom, and Scandinavia. Together, These markets account for a significant share of global production and innovation. Thousands of specialized suppliers contribute components ranging from glass and aluminum to sensors and automated ventilation systems. The supply chain stretches across continents. Think about this. The modern skylight industry supports hundreds of thousands of jobs worldwide when manufacturing, installation, engineering, transportation, research, and maintenance are combined. Behind every finished product stands an enormous network of miners, chemists, machine operators, designers, programmers, inspectors, and installers. Every skylight represents the work of countless hands. The history of skylights stretches back centuries, but the biggest transformation arrived during the last 50 years. Early skylights often suffered from leaks, poor insulation, and limited durability. Advances in tempered glass, low-emissivity coatings, insulated glazing, and precision manufacturing completely changed the industry. What once served as a simple roof opening evolved into a high-performance architectural system. Did you know that some advanced skylights automatically open and close based on temperature, humidity, and weather conditions? Built-in sensors communicate with control systems that help regulate indoor environments. What seemed futuristic a generation ago now operates quietly above our heads every day. Technology continues to redefine what a skylight can do. Did you know that a large commercial skylight system can span hundreds of square meters while supporting significant wind and snow loads? Engineers designed these structures using sophisticated simulations and structural calculations. The amount of force these systems can withstand often surprises even construction professionals. And here's another astonishing fact. Some high-performance glazing systems block large amounts of solar heat while still allowing abundant natural daylight to enter. That balance helps improve comfort without sacrificing brightness. It sounds simple, but achieving it requires decades of material science and engineering development. Looking ahead, the next decade may bring even more dramatic changes. Researchers continue developing electrochromic glass that changes tint electronically, integrated solar energy systems, smarter sensors, and improved insulation technologies. Future skylights may actively generate electricity while controlling indoor comfort automatically. The roof window of tomorrow could become an intelligent energy platform. From a grain of silica sand to a precision-engineered architectural product, the journey of a skylight reveals a hidden world of science, machinery, and human expertise. We followed raw materials across continents, watched furnaces hotter than lava transform minerals into crystal-clear glass, and stepped inside factories where robots and skilled workers build products capable of surviving decades of punishment from nature. Most people see only the finished window in the roof. Now you know the incredible story behind it. The next time sunlight pours through a skylight and fills a room with warmth and light, you'll understand what made that moment possible. Hidden behind that simple beam of daylight are mines, furnaces, laboratories, advanced robotics, global supply chains, and generations of engineering innovation. And perhaps the most remarkable part is that this extraordinary technology quietly performs its job every single day without demanding attention. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.